Hello there. My name is Eduardo Benavides, and this is my final presentation for my final report for my final project for CSE 546. Now, this is the continuation of a progress report that I did a while ago, but pretty much what they accumulate to is me finding the best algorithm from starting from four classifiers and optimizing those four classifiers with obviously their parameters, but with scalars, PCA, feature selection, clusters, ensemble methods, and getting the best algorithm for the data set. That's the end goal here. And in the first part, in the progress report, I pretty much found the optimal parameters for each of my classifiers, and I started looking for the PCA number of components for each of them. So that's where we're going to kind of kick things off. But first things first, we're going to look at the clustering because that's a little bit more simpler to start with. So for clustering, in the progress report, I said I was going to test two numbers, and that was the number 300 because we have 256 features. I wanted enough clusters to fit the features, but also the optimal number of clusters that this plot right here gives me. And it gives me 21. So I do that. I test the two. Well, not exactly. For some, I did test 300 initially, but then in my head, I was just like, let's just pick a random number. So I did a random number between 256 and 300, picked 293. So that's what I tested. And so you will see the silhouette plots right here. Beautiful. And the silhouette plots show the quality of the number of clusters. And you can see that the 21 clusters definitely has a better looking quality. There's a lot more of, let me see how to phrase this. It looks like it's able to read the pattern of the data much better to have the least amount of overlapping. They got a lot of thick lines there and a lot of thin negative lines. You want thick positive lines, but thin negative lines, right? Possibly no negative lines at all. So obviously there's a chance with the 21 clusters that it'll do better. The 293 clusters, I mean, It they're very long, just like these lines over here, reaching past point 0.4, but the average, which is represented by the black line, is less than 0.1. Well, this is just less than 0.2. So overall, this does a better job based off the silhouette plot, and you do see a lot of negative lines, and you don't really see a lot of thick positive lines. All of them are pretty thin all around. So this does show that this is pretty much having a lot of overlapping problems, probably not going to be that useful. And the ARI scores kind of back that up. For 293, it's 0.0242, so 2% for 293 clusters. That's just better than doing random. That's just better. It's not exactly high quality, not exactly useful. So yeah, that's not optimal. For 21 clusters, we get 25%, well, about 26. That's better than random. Obviously, the little overlapping that is potentially happening here is enough to really cause a confusion in the agreement level of the clusters. So there's something wrong there. But if I were to just choose those two, 21 clusters would be optimal. But that number didn't feel right to me. All right, 25%, 26% is too low. So I made this. Now, this is similar to the SSE versus number of cluster chart, except I did 1 through 300. And the peak right here, orange line, is actually at 7 clusters with the ARI score of 0.5258. So that means it is doing better than both of them. And because it's doing better than both of them, it does a better job at actually reading the patterns that the data is providing. And so There's still room for improvement. Obviously, there's overlapping because it's about 40% off or 30% off from being a very good score, you know. So there's definite room for improvement, but it's able to read the data really well in order to cluster the classes together. And so this is probably due to the fact that there are only 5 classes. So really worrying about the features wasn't as important. And and in the data set, the 5 classes are, and I'm going to pull this up because I forgotten, are here: person, sign, bike, bus, car. Those are the 5 classes, and we have 7. So obviously, those 5 classes are easily fitting into these 7 clusters. So that means with the silhouette plot, we're probably going to have some very good quality, high quality, most definitely higher quality than this. And in Figure 4, it shows that very few overlapping, thick, long lines reaching to zero point 0.6. So the optimal number of clusters for this data is 7. That is what that was determining. Now, moving on to the classifiers. So I will not be discussing the optimal parameters for the classifiers unless necessary. So pretty much if they're not involved in the best algorithm I create, you're not going to see the optimal parameters in this report. There's no need to see it if it's not going to be used. So that's my thought process. But I did start with a KNN classifier, K neighbors classifier, and and from the progress report, I started looking at the PCA. And so this is a continuation one. So this is test 1 from starting at the continuation. I can see that from point 4 to point 5, there's probably where the PCA is going to be optimal for the KNN. And for test 2, you can see that at 0.946, that's where it's at, right? That little jump right there seems to be pretty straight. Then that jump, boom, back down, lower, just a better fit. So I picked 0.946 as the variance for the PCA, and that's for number of components. So that's for K9. I did use the variance threshold as a feature selection, but there wasn't much of a difference um, with any of the testing. So I didn't think it mattered. I can show you that one because it is. This is this. I like I said, I didn't really include it in the report because they are all the same. So if they're all the same, I guarantee you it won't matter. So read them and weave them, right? So that's why that isn't there. Moving on to kernel SVM follows a similar process. For there is a little bit more testing for the PCA here. For the PCA here, test 1 from the continuation, I noticed that from around here to the end, that's where we're going to have to zone in on, right? Obviously, not a lot of showing, but I think that's just because of how many points I'm looking at. So we zone in on that. And now we see a little bit more character. And I can kind of see that, all right, from about here on out, there's something there. So that's what I look at in test 3. And now I'm like, okay, from here on out, there's something there. Is it around this spot? Which it actually is because it's a 0.968, which is the optimal variance for the PCA for the kernel SVM. So, but this was essentially just checking, is it at this spot? It easily could have been 0.965, but it's 0.968, and at 0.968 variance, that is 20 number of components for the PCA. So that's for kernel SVM. For the feature selection, I used the F class of feature selection. So this is just a figure. There is another figure that I did not include because I am going to tell you that this is how pretty much everything before this section looks like. The changing between overfitting and underfitting, that's pretty much that section. And it pretty much increases to here. And there's a little bit after that as well. So that's why I focused on 100 to 200. And the best K value is actually 196. There's a reason why I'm telling you that, and might be a bit of a spoiler for what the best algorithm is. But that's what I found through this. If I were to obviously use this feature selection. Random forest, same process. PCA, I could notice from 0.4, 0.94 to the end, essentially. That's where I'm going to need to look into. That's what I'm going to need to zone in on. So, and from that point, I noticed, all right, 0.96 to the end, right? We're going to zone in on that. And from that point on, I was able to get all the marks, and it was just quite clear that 0.97 was the point to pick. So I picked that point, and I believe it gave me 26 number of components. So yeah. So for 0.97 variance for the PCA is 26 number of components. Random Forest had its own feature selection, but there wasn't really an actual difference in the scores. I Without the feature selection, the Random Forest has a shape with 256 features. I use all of them. And with the feature selection, it cuts down in half, goes to 128. But it still gives the same exact fit, essentially. So nothing crazy there. So I didn't really think it was necessary to put the figure in here. The last one was the MNB. You'll hear me call that MNB. And this one's a little bit more tricky because, as you can see, due to its not liking negative nature, we get some weird fitting. So obviously, I knew that from about this point on, we're going to have to look at. And I was correct. You can see at about 0.963, right there, right there. That's the peak, right? That's our optimal spot. So the best variance, which is 0.963 for the PCA, is 7 number of components. With the MNB, I used a mutual info class of feature selection. It is awful. Gives you awful results. I had to show the feature selection on this one because it doesn't get past 30%. It's terrible. So, no. At this point, I really told myself I want to avoid the MNB as much as possible because this is awful results. So, based off that, I'm ready to do the ensemble methods. And with the ensemble methods, I wanted to combine the classifiers into the 6 combinations it can get to, because if I were to repeat, then it'd be 24 different combinations. No, wouldn't be 24. It'd be too much. It'd be too much. We only need 6 to get every combination we need. And I combined them using the stacking ensemble method. And just out of pure curiosity, I just wanted to see what their scores were, their accuracies were, right? And they're not bad. They're all pretty good. Pretty similar too, which is interesting. But like I said, I'm looking at how the combinations do, but not with stacking, just that alone, but with the bagging and add boost ensemble methods as well. So with the bagging and add boost ensemble methods, the only thing I did in there was I included the scalar method. Now, most of the classifiers, 3 out of 4 of them, use standard scalar as the scaling method. MNB has to use the min-max scalar. So pretty much any combination with the MNB uses min-max. Uh, any combination that doesn't uses standard scalar. And so you'll see in figure 12, these are the bagging results. And so you'll notice there's some individual results here. That is due to the fact that for some reason the K and N combinations were not working, but K and N itself did. And due to time constraints, I did not have the time to figure out why that was the case. So these are the results of this. And if I wanted to look at the individual ones just by themselves, then I would be picking RF as the best bagging ensemble here. But I want to look at the combinations. In the combinations, the best result is the 4th combo, which is the random forest with the kernel SVM. You'll often hear me refer to that as the 4th combo. So I picked that for the best bagging option. Figure 13 is where I picked the best combination for the add boost option. And K&N, once again, did not work. Use the voice correct. K&N, once again, did not work either the combination and individually for the add a boost. So therefore, it's not in here, right? But obviously, the individual runs poor, 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 right? The best one is probably the Random Forest and MNB. But I do like the little bit of extra error this gives. I think that to me, if I understood correctly, it does help a little bit more with generalization. So that's why I picked it. But also, and I'll be honest, I just did not want to mess with the M and B feature selection. So I went with the fourth combo. So we're doing the fourth combo with add boosting and bagging ensemble methods. So that works for me. We move on to actually testing them. Now, what I do for testing them for the comparisons is I'm testing the scalars. I'm retesting, making sure that the standard scalar works for them, or if need be, we change them to the min-max scalar. I look at the number of components for the random forest and kernel SVM, which are 26 and 20 respectively. I also test out the feature selections for the random forest and kernel SVM on the add boost and bagging. And from those three tests, I just look at the accuracies. I I kind of optimize them. So this is what's happening. For the scalars, they both started with standard scalar, but min-max scalar gives a little bit of a better fit and a little bit of extra error for a better generalization, which is what I like. So both of them are now going to be using min-max scalar for the PCA number of components. Both of them have a better fit for better generalization with 20 components. So therefore, both of them will be using 20 as the number of components when using the PCA. For the feature selection, both of them liked the kernel SVM feature selection with the F class of feature selection. They just have a better fit, which gives better generalization, which means that's what they will be using for the final comparison. Now, when I do compare them, I look at the scores for the accuracy. I'm just going to call this ROC, the accuracy, ROC, and F1 measure, right? And in figure 17, you can see that for bagging, pretty good accuracy, they both do. It does have a higher test accuracy, but its ROC and F1 measure fit is poor. It's actually underfit. You don't want that. You want a good overall one. And Add Boost has that. Good fit for the ROC, almost close to overfit, but it's good. It's a good fit. And F1 measure, an even better fit. All right. Slightly lower in the test accuracy, but that's okay. And so because this is the case, the Add Boost is the best algorithm. So, in conclusion, the random forest classifier with these parameters right here, with the 104 number of estimators, 30 max leaf nodes, 10 max depth, 16 max features, 42 for random state. The kernel SVM, where the kernel is RBF, C is 10, gamma is 0.0001. You have 10,000 max iterations, random states 42. Combine those two with the stacking ensemble, where the meta model is the random forest classifier with the standard scalar, and then you put that stacking ensemble into an add a boost ensemble where it has 100 estimators. It uses this algorithm because the default algorithm was giving me a warning, so I had to change it to this with a random state of 42. It's used with the min-max scalar, F-class feature selection. This is the selection. And the PCA with 20 number of components. That's the best algorithm. Now, I did use this algorithm and tested it on 30 samples to predict what those samples are, as I said before, with the classes. These are the classes right here, right? And the results of those right here, obviously, duh. Results of those are here. Now, based off the testing accuracy from figure 18, I should get about 26 of these correct. And I'll be told whether or not that is a correct assumption. But overall, that is it. That's my best algorithm. And thank you for watching and listening to my final presentation. You have a good one.